Okay, so I think we should continue because time is. All right. So next speaker, last speaker of this morning is Martin Traizet. I haven't seen any CV available online. So.
What?
I haven't seen any CV of you available online.
There is nothing much to say. So.
And then I can only say that because I met my first time Martin long time ago in '96, I think, in Impact, maybe. Yeah. And he's currently Maître of Conference at the University of Tours, and he's a frequent visitor of Granada, say. And very happy to have him here. His talk will be about loop methods for harmonic maps in sphere and hyperbolic space.
Yeah, so I'm very happy to be here. So Granada is probably the place I visited most often. So I was first here for, I think it's 1989, for my first international conference by Granada. And so it was organized by Antonio and Montiel, I think. Remember, I think it was 89?
91.
Maybe.
You were there?
Yeah, but I wasn't talking, I was just, and there was a visit with the Alhambra in the bus. I was sitting next to Robert Osson, so very intimidated. So I told him, I'm reading your book on monomorphs. Okay, so I changed my title 2 times. Maybe I tell you my first title was on the enclosed volume for CMC surfaces. So let me tell you what I wanted to talk about, and then. So the point of this talk is to talk about this loop group methods to construct CMC surfaces, say in S3 or H3 or in space forms, or more generally harmonic maps. So they are nicknamed like DPW method for Dorfmeister, Petit Wu. So they are, what's the loop group method? So it's something which is somehow like Weierstrass representation from some holomorphic data with your Riemann surface. The process to compute some CMC immersion into, let's say, S3, H3, S3 of course. Sort of similar to Weierstrass representation, but much more general. Is it okay if I write here? Yeah. So the point of this method is they are not very explicit because inside is the loop group decomposition, which is not explicit at all. So you cannot really compute things. So it's important in this method to still be able to compute like area of your surface in terms of your holomorphic data directly without having to compute the surface because you cannot, right? So we do have, so I'm talking about work, I should have said, yeah. Although I'm talking about this joint work with Sebastian and Wim Heller, except in fact I'm mostly going to talk about each newspaper. But so the thing is, can we compute the area directly in terms of this holomorphic data? And the answer is yes. Then can we compute the enclosed volume? So let's say I have a CMC surface, a closed CMC surface in a free sphere. It'd be nice to be able to compute the enclosed volume, right? And we do have such a formula, but that's new. So last year when I came to Canada, I came basically every year, we didn't have this formula. Now we have this formula. So with these 2 formula, we can sort of study isoperimetric problems, right? In the ratio. With this method, and we have a project, an ongoing project to solve some question about this asked by Antonio was. But this is not finished yet. It's not right yet. So 6 months ago, I want to talk about this. And that was my title, but it's not finished, it's not on archive yet, so I cannot talk about this. So I have to switch back to our previous paper, which was something, application of these loop proof methods to equivalent harmonic maps into H3, which is basically what Gabriel had talked about, and application to the so-called non-abelian Hodge correspondence. So actually that would have been very appropriate following Gabriel's talk. But, okay, but the thing is, I didn't know that. And so that was my second title, but then, so like, loop proof method for the non-abelian Hodge correspondence. But then I realized there are many students in this room, the summer school, so I decided maybe it's wrong, but I decided maybe the best thing to do is sort of give an introduction to these loop methods from the point of view of Hitchens construction. So that's what I'm going to do. So essentially, I will spend most of my time on point 1 and 2. So, and it's going to be basically on the board. And then I will, show you a few formulas and just to show you what you can do with this method, right? So point 1 is basically hitching, and the DPW method, so Dorf-Meiter-Felix group, was developed independently of the Hitchens theory. But in fact, somehow, when you see it from the point of view of Hitchens theory, it's very natural. It's like the trick to construct this solution to step duality equation. So let's start. So what's, oh, and I should say, I'm going to explain the Hitchens theory in S3. It's very similar to H3. So the reason to choose S3 is because it's simpler. Why is it simpler? It's simpler because S3 is the leap group. It's just SU2. So that makes it simpler, and H3 is not. Second reason is there are closed minimal substances in S3. There are no closed minimal substances in H3. You need to use equivalent maps, so this introduces some additional complication. So for just pedagogic reason, it's simpler to explain things in S3. But the theory is really similar, and each has two papers, one in S3, one in H3. I'm not even sure which one came first. Sort of them at the same time, I think. So let's start. So we start with the Lie group. So in fact, most of what I'm going to say in this point 1 will be true for any Lie group with a B invariant metric. We take SU2 because this is S3. So remember, SU2 is a set of two isometries of this form. Right? So we split two complex numbers. So if you identify C2 with R4, you really recognize the three sphere, right? So if you compute the metric, the p-invariant metric on this group, you can compute this formula. Then we take the compact Riemann surface, and we consider a harmonic map from the compact Riemann surface to three sphere. And we want to somehow formulate this harmonic map equation in terms of connections. So first of all, what connection do we have here? So first of all, the connection, the Levi-Civita connection on G. So that's an exercise that you find in Dokarmo's book, Riemann geometry, which everybody has read, I think. So on any Lie group with a B-invariant metric, the Levi-Civita connection is the average of the two connections that you obtain by left and right trivialization. So what does that mean? What is gamma L? Nabla L. So I take two vector fields. What do you do? So at some point G, so G is the point in SU2. So you translate by left multiplication to the tangent to the Lie algebra. So you multiply on the left. Take Y. You multiply it on the left by G minus 1 to put it back to the Lie algebra. Then you take the derivative with respect to X of this, and then you translate it back to G by again multiplying by G. So this is how you define your connection. So it's a connection which, if you trivialize on the left, is just trivial connection. So if you expand this, what you get is just dxy minus d dg minus 1. I have notes. Just to avoid making mistakes, right? And the nabla r by a similar computation, it's the same, but it's not right. Correct? Yeah. Okay. So the Carnot says that Lilith interconnection is just the average of the two. And now Hitchin writes this equation, and when I read Hitchin's paper, I was surprised by this equation. Nabla R minus Nabla L is different. He writes T minus 1 dt. So this is surprising because if you take the difference, this is not equal to T minus 1 dt. I mean, it doesn't work. So why does this equation mean? Well, the first thing to understand is this equation is written in the left trivialization, right? So this equation here, what is it? Okay. I'm talking about this equation. This is written in left trivialization. So this means that I'm going to do an xy minus r. And I write this in left trivialization. So I put g minus 1 here. Okay, so what do we get? So this cancels, right? And now we get a bracket. This. Okay? But this is just y with the left trivialization, right? So what you can rewrite this by saying that nabla r minus nabla l is just g minus 1 dg applies to y written in left trivialization, right? So this is written in left trivialization. We're not quite there here because there is a bracket. So how does it get rid of the bracket? Well, it's very natural. Everything here is the Lie algebra, and in the Lie algebra, the multiplication is the Lie bracket. That's the natural operation on the Lie algebra. So this means that you can rewrite this equation okay? Just because it acts on vectors by the Lie bracket. So this is exactly typical of me reading Hitchin. Every line is like this. So when you come from the world of Riemann geometry, somehow you have to work out what does each line mean. And to me, it was painful. But if you come from some other world, like fiber bundle, this is very natural. So let me explain a little bit about connection on vector bundles. Which is somehow the prerequisite to read Hitchin. So, vector bundle. Okay, so what's so vector bundle? So here L is a manifold, E is a manifold, and so the mention, so the fiber are all diffeomorphic to some vector space F, which is called a typical fiber, which is vector space, fixed vector space. And all these fibers fit together into a manifold. So more precisely, you have local trivialization. What does that mean? So this means that to map P phi from phi minus 1 of u to u times f, you have local diffeomorphism like this, which essentially what this means is that, so your bundle, you have your manifold with the fibers, and this map here sort of moves it into the product, right? So it sort of locally makes your bundle into a Riemannian product, right? This is what it is. Okay. And of course, this stabilization have to be compatible in the obvious way, as usual in differential geometry. Okay, so what's the connection? So maybe first, what's a section? So section is a map from M to U, and the space of section is denoted nabla of E. So the typical example that you know is, maybe everybody knows about it, but as a student, I didn't, so I expect maybe you don't. Maybe you do. So the typical fundamental example is, of course, the tangent space to M, and the section are just vector fields. What's the connection? So a connection is a rule to differentiate sections. So here X is a vector field, so it's a section of the tangent space M, and S is a section of your fiber bundle, so it's a section of E. Right? So, and the only requirement is that it's of course linear with respect to the two arguments, but it has to satisfy the Leibniz rule, which is like this. Let's see. I want to write this. Yes. Okay. So maybe I should X plus S. So it has to satisfy the usual Leibniz rule. So here F is a function and S is a section. Okay. So that's what the connection is. So there are many connections, but the difference of two connections is actually a one form. So let's take two connections like this, like nabla and nabla prime, and the difference. So if you do this, what you'll see is that nabla x fs minus nabla prime s. This term cancels, so this actually is Newton's computation. So what this means is that the difference is actually infinitely linear with respect to the section, right? So what this means is it actually defines one form on M, this value into so this acts on section, so and right, this acts linearly on section, and so it's a one. So this means one form from M, but it's not usual one form. So it's a one form this coefficient into something. So here it's endomorphism of your vector. Okay, so now let's see what the so-called local form in a trivialization. So if you take a trivialization U phi, then your connection can be written as follows. So I transport everything into is a trivialization into this direct product here. So the connection can be written like this. So you can always do. So it's a little bit like what I did for the left and right trivialization. So how do I compute this? I trivialize S, so it's now in the vector. It's now inside this fixed vector space. So now it's just coordinates. So I can just take derivative. That's just the usual derivative. And by what I just explained, so this is the trivial connection in this trivialization. So what remains is a one form. So it can be written omega x acting on phi of x. And this is a one form mu with value in endomorphism of f by fixed vector space. And this is called the connection one. Okay? And what people do in this fiber bundle world is that they just write this. Nabla equal 2 plus omega. You write this. And what this means is that in this trivialization, the connection is given by this formula. Right? But so in each, when you read this, you have to understand it's already written in the trivialization, identity does the same. And you have to guess which trivialization it is. Okay? Now let me explain. I have no idea how I'm doing this time. It doesn't really matter. Because it's clear I won't be able to go to the end of what's planned. Now let me explain what's gauging. So gauging is just change of basis formula. So that's just change of basis, change of trivialization. So I take another trivialization obtained by multiplying by some matrix G on the left, depending on the point, right? So G would be section view Y symmetry. It depends on X. Okay, and I want to write the connection in this other trivialization. So I can do the same thing. So this is X phi prime of prime here is my other trivialization plus. So that the connection omega prime is going to be the connection one form in the other trivialization. Phi prime of S. Okay, but this is also equal to G phi S, right? And now if you replace phi prime of S by this and do some obvious just two-line computation, what you get is the formula for omega prime. So you get this formula, T minus 1 dg plus T minus 1 omega g. So this term is just a change of the usual change of basis formula, P minus 1 A P, right? And this one comes from the fact that G depends on X, so when you take the derivative, there's an additional term. So this is called the gauge connection, and it's denoted by the dot like this. Because this group of, this gauge group acts on the right by this formula. This is called gauging. But gauging is in fact nothing else than the change of basis, right? But somehow, this is called a gauge theoretic formulation, so I have to explain what gauging is, right? Okay, so now I have to explain something more. Because I want to explain curvature. What's the curvature of a connection? And for this, I need covariant external derivative. Okay, so it's denoted D nabla, and this goes from P forms on M with value in E to P plus 1 forms. So remember, these are P differential forms, but with coefficient in my vector bundle. And so it's defined, it exists, and it satisfies the following property. which is again a Leibniz rule. So if I have, so alpha S. So if I have a connection here, I can always write it as a sum of small blocks, small forms, which have this form where, so this is just the standard differential form, real valued differential form on my manifold, and this is a section. Right? So I'm just saying I can just decompose it into blocks. And so I only need the rule to compute this. So it satisfies Ts, alpha. So this is just usual one form, right? I just want to use maybe a wedge. Okay. Yeah, no, I don't need a wedge here because this is just not the form. This is just the usual. The D here is just the usual external differential, and then so you have this alpha wedge lambda s. So it's just this is like a one form because it acts on x. So you can think of it as a one form with values in E. Okay? So the covariant external derivative satisfies this. So for example, if you just reduce it to zero forms, so to sections, this is just nabla. So in particular, when equals 0, the nabla is just nabla. Okay? And let's see, I want to, so it has many, essentially the same properties as the usual algebraic properties of the usual external derivative. In particular, you have Cartan's mathematical formula. So, which is a formula to compute the external differential derivative on vector fields. So, let me write this formula. Cartan. And I'm going to write the formula, so I'm just going to write it in the case for one form, just because it's simpler, but you will recognize the formula. It says the following. So, I take one form, with value is fiber bundle, is vector bundle, and I take two vector fields. So this is a very convenient formula which you use all the time. So this gives you nabla x omega y minus nabla y x minus nabla minus omega x. So you've seen this formula for regular forms where now this is replaced by just lead derivative. This is classical formula, it's called Cartan's formula. You have the same formula except you have to use connection. Okay, so now let's introduce curvature. So the curvature is defined essentially exactly as the Riemann curvature tensor. So for a section, so the only thing is that for some reason the curvature tensor is not denoted R but F. I have no idea why, but it comes from physics, so probably later R means something else. I don't know. It's denoted F, but it's R, right? So it's defined by the same on the section. It's D nabla of S. So this is the one form with respect to X. So let's compute this, and you will recognize the formula for the. You will see that with this formula, we get exactly the usual formula for the Riemann curvature tensor. So I use this formula. So this is nabla x, nabla y s minus nabla y nabla s minus nabla x y s. So same formula as for the Riemann curvature tensor. And it's for the same reason, this is in fact infinity linear with respect to all three arguments by the same computation. So it is actually a tensor and it's antisymmetric with respect of x and y. So this is in fact a two-form on n into an homomorphism of E because it acts linearly on sections. Right? That's called the curvature of the connection. So the connection is flat if the curvature is 0, and this is the condition so that it's locally trivial. So the theorem is so nabla is flat, so meaning this is zero everywhere. Equivalent is locally trivial. So which means that there exists a gauge such that nabla, you can gauge nabla, it's a trivial connection. You can gauge, or say, no, that's a stupid way of saying it. Just means you can choose a trivialization so that in this trivialization, your connection is just no problem. So, okay, so, and most of this teaching work is about flat connections. So this is why I wanted to explain what flat means. I think I'm done with my background on. Yeah, so let's go back to harmonic maps. Oops. Okay, now we have this map from sigma or Riemann surface to this liquid. So so first of all, what is the pullback bundle? Well, it just means that fiber over x is just a tangent space at the image of x to G. So it's like you pull back the tangent space at the image of the Riemann surface, and that gives you a vector bundle. And the induced connection, well, you define in the obvious way. So nabla x of a section is going to be nabla. So I transport x to by df s, and this is taken for the Levi-Civita connection of G. So this defines me a connection of nabla. So there are two. So okay. So now you can think of df as a connection as a one form of sigma taking values into this fiber bundle. This is vector. Right? Because its values is precisely here. And so we have two equations. So the first one, d nabla df. So this is automatically 0, but in fact this is really an avatar of d to f equals 0. But let's write it using Cartan's multiple formula, and you'll see that it's here. So this means that xy. So this is nabla g df of x df of y minus nabla g df of y df of x minus nabla df of xy. What? I'm missing something. No. No, yeah. df y, but this is really the same thing as df of x df of y. So you see that this is 0 because the Levi-Civita connection has no torsion. So this cancels with the back. Okay, so you see this is just elementary. So now the other equation is how to formulate the fact that f is harmonic in this language. So it's formulated by d nabla star df equals 0. So here star is the Hodge operator sigma. So duality operator in this case. So let me remind you, yeah. So in fact, to introduce this Hodge operator, I would need to introduce a conformal metric on sigma. But the harmonic map equation is invariant by conformal metric, so I can just choose the metric I want. So in local coordinate, I can just choose, the plane metric on the plane, and then eta is defined by this. Eta dx is minus dy. Eta of dy is dx, and eta of dx minus dy is two forms. That's just one. So essentially, this on the dimension n manifold, it maps p forms to n minus p forms. It's a duality of that. Okay. So the Laplacian f is given. So I take this for granted because my time is running. So this is the formal adjoint to the d nabla thing. And of course, f harmonic means that Laplacian f is 0, but you can rewrite this using the Hodge thing, the Hodge star as this, d nabla df. Okay, so this has to be 0. So this formula here is the analog of the well-known formula for functions. I mean, this function, so I'm talking about function in the plane in two variables. So Laplacian is just uxx plus uyy, but you can write it like this: star d star u. If you just do the computation with this, you'll find that this is just uxx plus. So this is classical formula, and in this context of vector bundle, it's generalized to this formula. Okay, so we are there. And now, okay, we have written this, but remember, we want to write everything in left trivialization. So this means I want to pull back this to translate this equation to the Lie algebra. So when I translate df, it becomes f minus 1 df. Okay, so we're going to introduce, we translate this equation back to the Lie algebra. So this means you interpret df as f minus 1 df, and actually that's going to be 2 phi. Okay, so what we know, we do this because the connections are expressed in this left trivialization. So we have to compute everything in the left trivialization. So what you get is d nabla phi equals 0 and d nabla star phi equals 0. Okay. So I've proven this last equation here. Now I want to explain where does this equation come from. So this comes from the following. It comes from the fact that the connection nabla r is flat. So remember, nabla r is nabla l plus, so it's up there, plus, so this is 2 phi. When I mean, if I pull back by f, so here, I mean, I should say this is a pullback by f of nabla r plus 2 phi. But since the Levitard connection is in the middle, it's equal to this phi. So now, this connection is trivial, so it's flat. That's because it's a trivial connection, so it's flat. And there is a formula, so this is f nabla plus phi. And there is a formula when you have a connection to express its curvature in terms of whatever you add to it. It's given as follows. So it's the curvature of this connection, then comes the exterior derivative of phi, and then comes this funky bracket. So what does this mean? So how is defined this bracket with the wedge in the middle? It's defined and decomposed form as follows. So if you have alpha s wedge, so here alpha is again P form, but real valued, and S is a section. So gamma E, right? And I can always decompose the form into small blocks like this. So then this is by definition, you wedge the forms and you bracket the sections. Okay. So it's actually, I mean, you have 2 minus 5 when you do interpret, so it's actually symmetric instead of anti-symmetric. Okay. So that's the formula. So if you put back, so now, I mean, d nabla is 0, so you get the equation. The fact that f nabla is flat gives me this equation. Okay? So almost there, and we are arriving at each step to the equation. So we're just going to write this by decomposition. So phi is a one form. We are going to decompose it into the complex cotangent space. So maybe so this is in the 1-0 part. So it's a 1-0 form. So this means in local coordinate it's something times dz, and this is the 0-1 part, meaning in local coordinates it's like dz bar, right? This one I'm going to call phi. So phi is this guy, and then because, yeah, I should say phi. Where is phi? Phi is f minus 1 here. So this value, phi is a one form with value into the Lie algebra. Right? So this means that phi star is minus 5. So here, so 0-1 part is the negative of this form. That's because it's unitary. Okay. And now we write this equation in terms of this new quantity. So first of all, so phi, if I take the Roth star of phi, yeah, be careful, there are two different notations, phi small and phi capital. That's each is notation. So I didn't choose that. So this is minus I phi plus phi star. So from this you get that d nabla phi is d nabla of star 0. And now I'm going to decompose d nabla into its 1-0 part. So this is like the 1-0 part of the differential, and this is like the 0-1 part. So you get but this is automatically 0 because like d of dz is 0. So that's automatically 0. So what you get is this. This has to be 0. So this is the second equation, and the first equation is just writing the equation that the curvature is 0 in terms of capital phi. Let's just do this. So now, nabla is what is the equation? It's so this. What? No, I don't have to write it. One half. That's my previous equation that the curvature of R is 0. But you expand this. So phi, wedge phi is 0 because in busy form, tangent busy form, and wedge in busy form is 0. So you get phi star plus because phi wedge phi 0 for 1-0 form, and the same thing for phi star wedge phi. And this is symmetric. Oh wait, there is a minus sign, because I was getting the wrong sign. There is a minus sign coming from here. That's actually minus. Now you have to write. Oh, it's quite important. Why? Because in the hyperbolic case, you get the exact same equation with the opposite sign. So this is 0. So this is called Hitchin's self-duality equation. This name comes from physics, from the Yang-Mills self-dual equation, which is actually the analog in the hyperbolic case. So there are a whole lot of Hitchin's self-duality equations, and they are related to harmonic maps. Let's finish this by explaining F conformal. So when is F conformal? It's equivalent to the fact that, so I should say phi is called the X field. And the second equation, nabla bar phi equals 0, sort of means that phi is holomorphic in some sense. So in fact, d bar nabla is what's called the Dolbeault operator, and it defines a unique holomorphic structure on your vector bundle. And what the second equation means that phi is a holomorphic one form on this holomorphic vector bundle. Okay. So that's called the Hitchin's self-duality equation. Let's finish with the conformality. So what is the induced metric? So remember, so the induced metric is minus 1/2 trace of f minus 1 df squared. But this is minus 1/2. This is 2 phi. So this is minus 2 trace of phi squared. Okay. Minus trace of phi minus phi squared minus 2 trace. So you have phi squared plus squared minus 2 phi squared. But this is like dz squared. This is like dz bar squared. And this is like dz bar. So if you want conformal matrix, you think this term has to be 0. You just want this term, right? So this means that trace conformal means that trace the x field squared is 0. But by Hamilton, since trace is 0, trace of phi is 0, this is equivalent to the fact that it's determined 0 by Cayley Hamilton term. Okay, so we're done with Hitchens theory. So let's just rewrite this to make the link with this TPW method. Let's reformulate this in terms of families of flat connections. So I have this connection, I have this X field. I can define one parameter family of connection, nabla lambda. So this is just nabla plus lambda minus 1 psi minus lambda psi. So if you look at this, so you'll see that just because if you just do the same computation than this is 0, this is flat for all lambda, same sort of computation I just did, just give you again the self-duality equation. This connection nabla lambda is unitary for lambda in the unit circle. Here I should say lambda is a parameter, a complex parameter. Right? Because this is a unitary connection and I'm adding, this is unitary on the unit circle. And it's trivial. So lambda r, lambda 1 plus lambda plus psi plus psi minus psi star. This is lambda plus psi, this is lambda r. It's trivial. And lambda at lambda equal minus 1 is just lambda L, lambda minus 5. Okay, so we have constructed this family of connection depending on this parameter lambda, which has very specific properties. And the TPW method is just a recipe to construct such family of connections. So let me explain that. And I'm not sure when I start. 45. Wow. Okay, so let me explain you how to construct these families of connection using this loop group method. So what are loop groups? So loop groups are groups of functions from this unit circle to some Lie group. In our case, it's going to be SL2C or SU2. And so lambda G denotes the space of, so this is like an infinite dimensional Lie group. Lambda plus G is a set of positive loops, meaning they extend holomorphically to the unit disk in lambda. Oops. So this just means that here you have only positive, non-negative powers of lambda, meaning so this is the reason for the notation plus. And the thing is, in these loop groups, you have this so-called Iwasawa decomposition, which means any loop you can decompose as basically, so in our case, a unitary loop, meaning in this lambda SU2 thing, so this takes value to SU2 on the unit circle, times a positive loop. And this is essentially unique. Right? So this is the decomposition I was talking about. This exists, it's not explicit except in trivial cases. So this is a part of this TPW method that's not explicit, and the reason why we cannot really compute things very explicitly. Okay. So what the input data for this TPW method is what's called the TPW potential. So it's going to be one form with value into this loop algebra here. So function on the unit circle with values into, so it's just in trace 0, right? But they have a special property that, so they depend on lambda, but they have at most a simple pole at 0. So they have this expansion like this. It starts at k equal -1, you have the residue, eta -1, and then it's homomorphic, right? That's the input data. And from this input data, I'm going to explain you how to construct a family of flat connection of the required form. So this is the theorem. So you're going to solve the equation d psi equal psi eta. So actually, in the DPW method, psi equals phi. But then there's a conflict of notation with Hitchens, because for Hitchens, phi is the x field. So I changed the notation. So, but if you already know DPW, I'm talking about phi here. Just all enough notation. So you solve this equation. So of course, sigma is maybe not simply connected. So you do this in the universal cover. So then you define the monodromy along a loop along the element of the fundamental group. So let me remind you what this means. So what this means is that psi. So here, this is the action of the fundamental group on the universal color. It's just multiply on the left by the monotone. And okay, that's the monotone. When you go around the loop, you come back to where you started from. It's again the solution of the same ODE, except it's been multiplied on the left by some metric. That's the monotone. And you assume you have to make two assumptions. First of all, that so the monotony depends on lambda, because everything depends on lambda. You have to assume that this is unitary. The monotony are all unitary, and moreover, they are trivial, meaning plus or minus identity at 1 and -1, which are our special point, remember, in this Hitchin family of flat connection. Now you do this Iwasawa decomposition of the solution psi in F and B, okay? And you define this family of flat connection, nabla lambda is D plus F minus 1 dF. So remember, F depends on lambda, right? So this depends on lambda. That's why I write it F minus 1 nabla lambda. Then, in fact, and this is the trick, this is what the magic, it has exactly the required form. And let me explain you what, and probably I will stop there because my time is running out. Why does it somehow provide a solution to the self-reality equation? Well, that's not difficult. In fact, it's a few computations. Let's just do this. So the first thing to observe is that what is this condition here used to? Well, the thing is, by uniqueness of the Iwasawa decomposition, the monodromy will all go to the unitary factor. And the positive part I'm doing the Iwasawa decomposition of psi at this point, right? By uniqueness, because this factor is already unitary, all the monodromy goes to the first factor, right? And so this means that the B thing here is well defined on sigma, but F is not, the unit part is not, but it has a monodromy. Nevertheless, if I take omega is F, so that depends on lambda, F minus 1 dF, you see that when you do this, in F minus 1, the monodromy goes to the right, so cancel. So this is actually well defined and sigma. It has the same value at C and gamma point C, right? Because the monodromy cancel here. So, yeah, first good news. So this is a well-defined family of connection on my Riemann surface. Plus, F is unitary on the unit circle. So this is a unit family of unitary connection on the unit circle. Unitary. Okay, now you have to see that this has this very special form here, and that's a small computation. So let's take, to prove this, let me expand omega in terms of lambda. So omega depends on lambda because F depends on lambda. So I can write omega as the sum of omega k, lambda k, like this, series. But now let's differentiate. So d of fb, so that's fb times eta. So this is just, my differential equation, d psi equals psi eta. So it gives me df times b plus f db equal eta, and what you get from this is f minus 1 df equal, which is b eta d minus 1 minus db d minus 1. This is omega. Okay, and let's look like this. Remember, P is the positive part. So there are only non-negative powers of lambda. So this is holomorphic, no lambda minus 1. And the only place where there are negative powers of lambda is here, because eta as a residue is a simple pole. Right? So this means that omega k 0 for all k less than minus 2. That's I suppose a simple pole, just because the only pole that I can see here is here with respect to lambda. But now it's Hermitian. It's Hermitian. Omega is minus omega star. So omega k equals 0 for k greater than 2. So you see we have only 3 terms, and we can only read omega 1. It's here. So I have to take the coefficient of lambda 0, eta minus 1, 0 minus 1. And if you plug this in, you get this exactly this formula. And now what we have achieved here, we have constructed this family of connection just as Itchin, which are flat for lambda, unitary on the unit circle, trivial at lambda equal plus or minus 1. This comes from, oh, I should say, why are they flat? Yeah, I haven't said why they're flat. Well, that's obvious. Nabla lambda is flat. So that's just trivial connection gauged by F. Fine, but it's locally defined on M, on sigma. So this means that this connection is locally trivial. And the gauge is just F. So flat. Because flatness is a local condition. And it's also globally trivial at lambda equal to or minus 1. That's because this condition here ensures that at lambda equal 1 and minus 1, f is actually a well-defined function on my Riemann surface. Okay, and now if you unfold things, I mean, this Itchin self, I didn't say it, but this Itchin self-duality equation is goes both ways, right? It's equivalent. If you have a solution of the self-duality equation, you get a harmonic map. And the harmonic map is in fact the gauge between lambda equal the connection at lambda 1 and lambda minus 1, so it gives you this formula, and this is a formula that's in the DPW paper. It's called, from the DPW world, it's called the Simbo-Benko formula, but from the Itchin world, this is just the gauge from the connection lambda 1 to lambda minus 1. And finally, it's conformal for minimal surface, because remember, minimal surface into the tree-sphere, just a conformal harmonic map. Means so determinant of the Higgs field has to be 0, but the Higgs field is there, so it just means the determinant of this eta minus 1 has to be 0, which is the standard condition in DPW. Okay, but I could give you, I know, I should give you 2 examples, right? Because it's pointless to present a math theory without giving you, so let me give you 2 trivial examples and 1 picture and I stop. So example, so if you take eta on the Riemann sphere, what you get here is an equatorial sphere. If you take that's a 1. See? That actually gives you arbitrary immersion, which is actually the Clifford torus. And that's basically the only 2 cases which you can actually compute explicitly. So this is quite frustrating, right? Because we expect to do more. So I just show you a few formulas. So we've been able to sort of compute the Lawson minimal surfaces, which are somehow, after the Clifford torus, the next one is probably this Lawson surface constructed by Lawson by solving a Plateau problem here, you know, with the geodesic polygon and extending by symmetry as these families of surfaces. For G equal 1, it's a Clifford torus, so it's okay. And the idea was, can we compute this using these methods? And the answer is yes, somehow. It's not as explicit. So the potential we take So somehow, I mean, yeah, this is hygienous, but it projects. There's a J plus, the Riemann surface here is a J+1 covering of a 4-punctured sphere because of all the symmetries. So we can just write down the potential of a 4-punctured sphere and lift it up. Okay, and we have formulas. So here the xi are just function of lambda, which we have to determine, and then it's a simple pole at these 4 punctures, and this sign here encodes the symmetries of the surface. And I'm just not going to say much. I just want to show you formulas. What's going on? Yeah, so the thing is, you cannot compute explicitly these parameters here, but we can somehow solve the equation by implicit function and then expand them in terms of this parameter t. And we have formula. So you can contemplate this formula, and we can actually, I mean, I've only written the first few terms, but we can actually go to order 21 or so, and it gets uglier and uglier, but we have an expansion of these things here. And what's interesting is that you see that here some strange numbers show up, like zeta of 3, Riemann zeta function. And finally, with this, we are able to prove things like that. So somehow we can sort of compute the area of the Lawson surfaces, at least for large genus, as a series like this, with a coefficient. So the first one are quite simple, log 2, then 9/4 zeta of 3 shows up. And then all of them are, in fact, alternating multi-zetas, which are natural functions in analytic number theory. And we also know things like, this process, in principle, at first works for large genus because we solve the equation by implicit function. But we can actually show that this process works for genus at least 2.65. So of course, the genus is an integer. It just means that this series is written. We know it converges for G, so let's say G equal to 3. Okay. I should say, if you take G equal 1 in this formula, so we have computed this to order 21, numerically, right? We have numbers. So we can just plug in G equal 1. And we get, so this should give us the area of the Clifford torus, which is 2 pi square, and we get 2 pi square with an error of 10 to the minus 3. So it's very suggestive that the series actually converge up to G equal 1 and more. But that we cannot prove. Anyway, so with this, we can prove that, in fact, the area is increasing for all genus, which, is concrete results that we were able to achieve. Okay, I will stop there. So I'm sorry I didn't talk at all about the non-abelian Hodge correspondence. So certain people certainly are frustrated, but yeah, I'm sorry.
Question from no questions. So then, thank you again to Martin, and we will start again at 5.
Muy bien. Dice que puede encontrar una fórmula.
Volume?
You say that you can find a formula for the volume.
Yeah, that's it.